So, today we are going to start one of the other important aspect of calculus, integration. Many of you know possibly it is a reverse of differentiation and blah 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 stuff, but integration as the way we know it had started not exactly in the way we think, taking the antiderivative and this and that. Let us go back and think in the old classical style, in the time of as if we are in the time of Newton and Leibnitz. So, Newton and Leibniz, I do not have to obviously tell you who Isaac Newton is, and Leibniz was also a German mathematician and philosopher who actually had developed the signs dy, dx, this use of these signs of calculus, and he started calling them derivatives rather than fluxions, which were called by Newton, and there was a lot of fight between who is the true inventor of the calculus, and Newton made sure that the Royal Society guys gives him the credit. So, whoever it is, so we are going to talk about what integration is. The integration actually comes from a very old geometrical idea which was known to the ancient Greeks. So, if I take say a closed body like this, and I ask what is the area. So, if I call this body as A, so I ask what is the area of A. I ask now what is the area of A. Okay. So, now if I ask this question to many of you, you would say okay, something you try to give something inside, something like that. But truly speaking, area is a very intuitive notion and it's not so easily definable. So, what we want to say by the term area is that we are trying to give a measure to the space enclosed by this curve. And the Greeks had defined areas of certain objects, and with those elementary objects we can talk about areas of much more complicated objects. For example, if I look at this area, if you take a polygon, so how do I know the area of a polygon? Take a point here, join all the sides with this point which is the center of the polygon, and then you know the area of triangle, you compute the area of the triangles, and you know add those areas and say okay, this is the area of the whole polygon. Now, what would happen if not such a regular body is given to you? What are you supposed to do? If I get a body like this, the best thing is that if you take a transparent body or on a paper, actually put a graph sheet over it, a grid. So, essentially, for example, you would put a grid around it, where each grid has the same length and breadth, so it is square. I am just drawing it, may not be very clear. So, what I would like to do? I would first like to look at these these squares which are all inside, completely inside the body. And we know what is this, suppose they are there each of side s, then it is s square. So, if each of them is of side s, the squares, then if there are n such things here, then you have n s square as the area that I have just covered. But then I also want to take some rectangles in which the body is contained, but of course I will not take a huge one, maybe the nearby ones. So let me take those rectangles which they are just slightly outside the body, that is the body is contained in it. So maybe I will mark these rectangles. So these are the dots. So here we are actually, this is how mathematics is developed and this is the way it should be learned. So this for example, this one was slightly outside the body, so we had not taken this part. You see they are slightly outside the body, so we had not taken it inside. This is completely out. So we are basically covering these rectangles which overlap with the body. We will not cover any rectangles which are away from the body, which do not overlap with the body. So only those which have an overlap with the body. If for example here there is only one, say one point which is passing or a little bit, so we take this one. But we do not take this one because it does not overlap with the body. Now, or neither we take this one because it does not overlap with the body. Now the dotted region, suppose there are m such rectangles, so the dotted region, has those rectangles which are overlapping. So now let m be the total number of blocks, that is both the dotted region and the region which is already inside. So I consider those which is already inside and those which is inside plus those which are overlapping. So m is the number of total blocks which are intersecting with the grids, square blocks which are intersecting with the body. So n is the number which is those blocks which are completely inside the body. So this has an area ms square, s square is the area of one square. So the area of the body is bounded by these two quantities. And then I can make this area, I can choose my SS in such a way, you know that this would be obviously bigger. I can make them, I can choose this S in such a way that from both sides this would become smaller and this would become larger. The more rectangles would come inside the body and hence finally they would converge in the limit to the area. That's essentially the concept. By the way, this concept is what Archimedes used to find the area of the circle and hence also the area of also the number pi, right. So we are not going to maybe we can discuss a bit about that if you wish. So let me just this is a good thing because it's not always there is not always a chance that you speak about how you talk about an area of a circle. So this is how Archimedes did it. So this is one method which I take from the book by Corner called Calculus for the Ambitious, Corner's approach here. But this is an approach which I have not seen in any text. I will speak out the Archimedes approach later on. So you might ask me why are you intending to do all these things, because that will give you a fair idea of how I am developing the idea of the calculus, how developing the idea of integration. Because integration is a term where we are trying to find a area under a curve and bounded on three sides by a rectangle. It is like, you know, something like this. It's as if, you know, the water is flowing and in this section, you know, water is flowing in the river and you are looking through some mirror and the water is flowing by you, and then how much water is there that is passing by you. So these are the questions. Integration helps you in answering such questions. Now what is Corner's approach? Corner's approach for computing areas of the circle is that you take a circle. My drawings may not be all correct, beautiful looking, but what I do, so this is say of some radius, say r, doesn't matter, radius 1 also doesn't matter, even radius 1 doesn't, if any you take it to be radius 1 doesn't matter. So what do? You cut into slices, which basically it's a cake cutting thing. So you cut it off into slices. I am not going to waste my time completely cutting them off. So if I cut them off into slices, then I can actually write down the slices like this. I can arrange the slices like this, basically arranging the cakes on the plate. And so on. Okay. So there are all these slices here. Now, how do I use an approximate idea? See, if these slices are very small, that is okay. So let me. So what I can do, actually what I can do, looking at the circle as an body which is closed by a curve, I can simply do the same thing. I can write the grids and do the same story. So if I put grids over it, so first I cut it into this and arrange it like this, and then I put grids in the same way, and I do the same thing with the size S. I do the same thing. So I put the grid, and then you see what happens is that I can simply say that again in the same way, ms square is bigger than the area of the disc, the circular disc, and this is greater than ns square. But I can choose s in such a way that if you give me any number u, right, any positive number u, if you take any u greater than 0, then choose s such that what would happen? That u is controlling the growth of this difference. U is controlling the growth of this difference. U could be greater than or equal to, doesn't matter. So this u is now controlling the growth. So this difference cannot be, if I keep on choosing the s, I can make u smaller and smaller and smaller. That is, I can push u towards 0. So this difference should become smaller and smaller. I can make u smaller and smaller, so that this difference, the difference between these two becomes smaller and smaller and finally converts to the area. That's the idea. So now if I put a magnifying glass which magnifies, makes this bigger. So instead of radius 1, I have radius r. So I have a sphere of radius r. Okay. So what is, so the area of the sides of the squares now gets magnified by an amount r. So everything is dilated by an amount r. So now the area of the squares, the sides would now become rs if it is dilated. If it is dilated, I will dilate by an amount r, the squares would become rs. So what would happen? Area of disc of radius r now is bigger than the same, you could have the same m and n, only the dilation has taken place. It is n, now it is SR is the size So, SR into SR, S square R square. So, this inequality continues to hold, right. And of course, from here you will find that U R square okay. So, what you have done? So, area of the disk of radius R, what is this? Basically, I multiplied by R everything. So, I can write this statement, this particular statement, this one, this line can be now written as M S square R square is bigger than R square times area of disk of radius 1. So, this is a disk of radius 1. So, that is a disk of radius 1 is also called a unit disk. So, area of unit disk which is greater than N S square R square. So, this is what I will have. Okay. So, what we finally conclude from here? We finally conclude from here is that the area of disk of radius R is equal to R square, the area of unit disk. That is what we have concluded from our discussions here. Now, how does it help? Now, if you look at this thing, this some sort of this cake's been put on the table. If you look it from the top, that cakes would look like that, and it can be viewed as some rectangle. Very roughly can be viewed as some approximation of a rectangle. Not really, but let us just view it as some sort of an approximation of a rectangle. And then, what do I have? So, this is the length R, and what is this? What is this part? So, this part comes from this part of the circle. The bulge that you see comes from this part of the circle, this sides of the cake. So, if I look at this thing, so what do I have? These are nothing but parts of the circumference of the circle. So, this length, if I have laid down all these cakes side by side, so this side is nothing but roughly its perimeter, half of the perimeter of the circle. So, this whole thing R into perimeter of disk of radius R is by 2. So, this is this thing. But what is this? This is nothing but the same as the area of this circle, area of the disk, because we have cut out the cakes and light them down. So, they must be the same, give me the same area roughly. So, I am just writing rough, but this is just an approximation, please do not. So, it is really not a rectangle, so there is a roughness, so it is approximately this, it should be like this. So, area of this part I can call this as area of cake, say area of cake is roughly this, but this is nothing but the area of, is the product of the sides of R. So, this is roughly the area of disk of radius R. Now, this is nothing but r square into radius into area of unit disk. Now area of unit disk is a fixed quantity, it is a constant quantity, and let us call that constant quantity as pi. Now, so area of the unit disk, now r square into area of the unit disk is roughly this, right. So perimeter, now let us, so area of the unit disk is constant and let us call that constant pi. Of course, you can ask me how this pi came, we will tell you a bit, I will give you some idea. Area of the unit disk is pi, so some constant, right, it is just a constant. So let us call it constant, just call it constant if you want to, and I am just writing this as pi because we already know something about it. This is a constant number, right, because obviously it cannot be changed. Right? So what does it mean? It shows that perimeter of disk of radius r into r by 2 is equal to, so as you do better and better approximation, in the limit this gets better and better, because as you make this thing smaller and smaller, the approximations become better and better. So this approximation finally, let us say, becomes equal. These are all just approximation arguments, by the way, and this is nothing but that r square into pi, the constant. Now what does it mean from here? It simply says that the perimeter of disk of radius r is equal to, or the circumference of the disk of radius r, perimeter is same as the circumference, is 2 pi r. So which means the perimeter of the disk divided by the diameter of the perimeter of the disk of radius r divided by the diameter is always constant. So whatever be your radius r, it does not matter, the ratio of the circumference by diameter is always constant, and this is done because you have some idea, you are using the idea of area in just this particular way. It is the area idea that the way you, so you are adding, you know about the area of square, and once you define that, you can do a huge amount of thing, and that is exactly what we are going to do with functions. And so the question came when calculus was developed that sometimes curves, part of it, for example, can be defined as some function, a continuous function. Then how do I go about finding the area under a curve of a function which takes non-negative values between 2 points? So that is exactly what we are going to now discuss. It is the same story that we are going to write. There are several ways to look at it, and let me tell you what are the ways. How are you, see, it is the same idea that we will go through. You can put the squares, but I will not put squares, we will just deviate a little bit, make ourselves more comfortable. So here is my x axis and y axis, and here is A, here is B. So here is the line x equal to A and line x equal to B. So let this be a curve, a nice continuous curve. In those days, these sort of curves were what people were using. They were not talking about discontinuities and all these things. By the way, a huge amount of mathematicians have actually devoted their lives to this. So we cannot just in one session really finish what the integral is. So we will actually split it into 2 sessions. So the Newtonian style in 2 lectures, maybe one more, doesn't matter, and then we will go to the next step, which was given by Riemann in the 1800s. So, this is what was going on in the 1600s, 400 years ago, and that is amazing. Huh? So, not 400, 350 years ago, I would say. The beauty of mathematics is that it endures, it is permanent. Theories in physics change, theories in chemistry change, but in mathematics things endure, and that is the beauty actually. Now, how do I, am I going to again draw rectangles? It might not be always good idea to have rectangles, but then we are not being able to use the function value. So, we have to make use of this function value that is known to me. So, okay. So, this is the graph of the function y equal to fx. What I will do, I will partition this into say equal parts, a plus 1 by n. So, I will take a nice division which is called b minus a by n. So, I will make equal divisions of this. So, a plus h, a plus 2h, a plus 0h is this, a plus 3h, and so on and so forth, and this is b is a plus nh. So, what I do is I draw rectangles. I am assuming they should be equal. Whatever. Please forgive me for unable to write two things equally, but doesn't matter. The idea is the main thing. So, I draw a rectangle here, and then I take this side A and draw perpendicular on this line. So, I construct one rectangle. Similarly, I take this one and construct another rectangle. Another way I can construct another rectangle and go on. So, you see, and so on and so forth. I am constructing the rectangles and going on. All the rectangles has the same . So, now what is the height of this rectangle? This f of a. What is the height of this rectangle? F of a plus h. What is the height of this rectangle? F of a plus h by a plus 2h. So, what I am see, so what when I club the areas, what do I have? I have this. So, f of a into h plus f of a plus h into h, because these are all h, plus f of a plus n minus 1 h into h. So, this is my area, this rectangle, area of say rectangle, total rectangular region which I call Rn, area Rn is this. Now, I can make my n larger and larger. So, this h becomes smaller and smaller. So, these are some leftover areas, you see some overestimation and some underestimation if you use modern language. So, it's underestimation, here there is a little overestimation, and then all are underestimation. So, some area is not there. So, if you have more small h, you have more and more areas covered in the same way. So, what is this? So, you can write this as f of a plus kh, right, where k is equal to 1 to n minus 1. Sorry, k is equal to 0 to, and that into h. So, that is exactly what I have. Now, what But we have said that area finally comes out in a limiting sense in what we are doing. Now you say, okay, well, where is your overestimation, underestimation in that form? What did you do? Okay, doesn't matter. We can see that if we just keep on doing this and make n increasingly large, this underestimation or overestimation gets smaller and smaller and smaller and smaller and smaller. So ultimately, the area under the curve, so area under f x is limit n tends to infinity summation k is equal to, as I told you, everything are names given to special kind of limits. And this limit is what? This limit is what we called the integral from a to b of fx. So what is this? It is nothing but an extension of this sum. You are elongating the sum, you are just making the sum look this. So because it is now n is so large that there is no discreteness, it is almost continuous, it is a continuous sum. So if you continuous sum of integrals will give you the area. So this means so here if the this is we are only considering functions which are non-negative, because functions which are non-negative my area is very clearly defined. Functions which are either fully negative also the area is clearly defined, but function which is both negative and positive, then there is some issue we really need to take care. So this is f of a plus kh into h. This is what we are doing, this is what we have, this is the definition of the integral. Now I can say I can get back the same ideas in a slightly different way. Some people would say, okay, let us do something else. Give me those estimations, man. You have to understand, you have to use some property of a continuous function. If it is a nice function, use its properties. One of the main properties of the continuous function is that it is an upper bound and a lower bound once it is defined over a closed interval, right? So then so you have the same So now what we will do, this is the idea which we will later on use when we will talk about Riemann's approach to integration, is that okay, let us make the same divisions a plus h. Riemann would generalize this approach also, this approach of dividing a plus some kh and dot 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 a plus nh. So just divisions. So at every division you see which is the maximum value of the function, which is the minimum value of the function. So first consider the maximum value of the function, this, and create with that the rectangle. Here you see the maximum value, create with this the rectangle. You will see this, these rectangles are overestimating maximum value. Here also maximum value is here, and here the maximum value here to here. It's here, so you see the rectangle is overestimating. Here the maximum value is this, so this would be the rectangle. So the rectangles finally are overestimating. Similarly, you can draw. So what you have taken, the maximum value and the minimum value. I will draw this line, this is x equal to a, this is x equal to b. maybe I'll draw the same sort of curve. Let me look at the curve and draw same sort of curve. So now we will do the same division, a plus h, a plus 2h, a plus 3h, a plus kh, and so on. So take the lower value. So you see this rectangular area now is underestimating, some area is already left inside. Now you take the lower functional value on the whole interval, because there will be a bound, and do it. This function is a plus 3h is here, and then it's again the lower, now the lower value is slightly here, it's like this, and here again the lower value is here, and it's like this, and it just goes on like this. See, this will be all underestimation now. Now what is this? What is this integrals that if you want to? So what are those what are those final integrals basically? Maybe this line should be b. So what are these? So how do I calculate the area of this? So the function overall has capital M as upper bound and small n as the lower bound. And now how would I calculate the area of the overestimating rectangles and underestimating rectangles? So overestimating rectangles, we took mi, so is the upper bound for, so m1 is the upper bound for this, and so on and so forth. So what we did, m1 into h plus m2 into h plus mn into h. But what is this ultimately, these rectangles? These rectangles, this rectangular area, and this rectangular area is, suppose I take, no, let me capital M1, capital M2 and capital Mn. So these are the maximum values over these intervals, and these intervals are close intervals over which the function is continuous, and hence they will have maximum values, which is obvious. So the smaller one, n, is the lower bound, so it's n1 h plus n2 h plus n h. That is what you have, and the integral, the actual area is lying between this value and this value. So it's n1 h plus nh is less than equal to integral ab, because the area under the curve, we are not looking at only non-negative functions. Please keep this in mind. And then this would become, so this is the classical way of doing the stuff, m1h plus mnh. Now all this n1 into nn is finally bigger than the actual bound. One of them is the actual bound over the whole. So I would have this whole thing is actually bigger than n of h, right? So I put n, h, but if I add these h's up, so what will happen? I will have n of nh is less than equal to integral a to b, where n is the lower bound of the function over the whole ab, and m is the upper bound of the function over the whole interval ab, and this would be less than, m n h. But what is nh? From my definition it is b minus a. So n times b minus a is less than integral a to b fx dx is less than equal to integral, is less than equal to m of b minus a. So because you will sum those, so what you have done here, all these m1, m2, mn are actually less than capital M, because these are all over the interval, and m is over the maximum over the whole, and n is the minimum over the whole, so the lower bound over the whole. So that is, so you see we had used this limiting idea to know that finally we will get to the area, whatever is the case, and this is exactly the way what we had done with those squares on a closed of a body surrounded by a closed plane body surrounded by a closed curve. The way we tried to measure the area of that, the same idea has been put here. You see that body's area is lying between the two things. Actually, if you look back and look into Archimedes' style of finding the area of a circle, what he does is takes certain points, divides the perimeter equally, means each of these arcs has equal length, and then he joins them, he slices them like the cake, but does something else also. So this is, so historically integration came much earlier than the notion of the derivative. Now he joins these two points with the chords, the adjacent points with the chords. So what you get in is a polygon, but some areas are left out, some area of the circle. So in the next step you will increase the number of points and again have a polygon well which will cover further more area, and keep on going, and doing so you will cover the whole area. So what happens? How do you find pi? That you have already known that the circumference and the radius of whatever circle you take will give you a constant number. So you take any circle, you can do the experiment home, take some 2-3 circles and find the diameter and their circumference, put a thread, take a thread and put it across the diameter, now just lie it along the circumference, take it out, gradually make it straight and see what is the length on a scale, and when you take the ratios you will see more or less that you are getting the same number. But because obviously there will be errors in your measurement, because once you measure something you have to admit there are errors in measurement, so you cannot get exactly pi, because pi's value cannot be exactly calculated because it is an irrational number, but you get somewhere an approximation of pi. So here is the fun. So here you see how this, so idea of integration came historically much earlier than the idea of differentiation, and that is why this is very important that this is the way first it has to be introduced. Now once this is known, how do we go from here to arbitrary functions? That is what we will discuss in the next class, and we will put some formulas in the next class, and then we will use actually this idea, this simple idea to actually evaluate in integrals. For example, I will evaluate for you an integral of the form, or maybe 0 to 1 t squared dt. Very simple function, fx is x square. But mind you, as Corner mentions, that this, to evaluate an integral of this form, big minds like Cauchy, Legendre, Wallis, Euler had given their time. So it is not a joke. It is not so easy to actually evaluate. You just know this is a definition, and it is not easy to calculate limits like this. But how are you? So this is the only way you really have to evaluate an integral. So every integral of this form had to be evaluated in this fashion, and it was also not easy. And that is what we will do in the next class. You will see, we will end with calculation of this one, and but first telling you how to get on with things which are, how to go from non-negative to the general one. Thank you.